Okay, we find ourselves at the end of the unit, Unit 9, Objective 8, applications of logarithms, and this time it's specifically related to something that's near and dear to all of our hearts, and that is money. Let's take example number 1 right here. Jamie's grandparents deposited $10,000 into a savings account when she was born. The interest compounds monthly at 5% annually. How much money is in the account after 18 years? Well, we're going to use this formula right here, and hopefully you have in your notes what all of these different notations mean, but even if you don't, I've got them right up here so you could jot them down. They're also in the PDF. So let's start with the A, the ending amount of money. Well, that's what we're trying to figure out. So A is still A, but then everything else is known. The principal amount, the initial amount of money they put in was $10,000. 1 plus. The interest rate is 5%, so we're going to call that 0.05. It's compounded monthly. Well, there's 12 months in the year, so that would be 12. And then the power that it gets raised to is n times t. So again, if it's compounded monthly, that means it's going to be compounded 12 times during the year. And if it's for 18 years, then it's basically 12 times 18. Now, next thing, let's A equals 10,000, 1 plus 0.05 over 12, and the only thing I'm going to do is simplify 12 times 18, and that becomes 216. Now, everything else from here can be done on the calculator. I'm going to do the parentheses first, so 1 plus 0.05 divided by 12 equals that number. Now, I'm just going to keep that number in my calculator. See where I'm going with this? I'm going to keep that number in my calculator, and I'm going to raise that number to the 216th power. And now I get that number. I'm going to keep that number in my calculator, and I'm going to multiply that number by 10,000, and that's going to be my final answer. The amount of money that's going to be in that account is $24,550. And approximately 8 cents. So that would be the ending amount of money in that account. The next example is similar to what we just did. In fact, we're still going to use the same formula. And an initial investment of $8,000 grew to become $18,504 when it was invested at 6% with semi-annual compounding. That means it's only going to compound twice a year. How many years was this money invested? Like I said, same formula, similar setup, but it's got a whole lot more moving parts in this part of the problem because, for one thing, we know how much money we ended up with. So we know the A value is 18,504 equals. Well, we know how much we began with, too. We know the principal, 8,000 times 1 plus. We know the interest rate was 6%, so I'm going to put 0.06 right here. And we know the number of times that it's compounded per year is 2 because it's semi-annual compounding. So I'm going to put a 2 right there. And that means I'm also going to have a 2 right here. But the one and only variable we don't know in this problem is the length of time. How many years was it invested? So the t is the variable we want this time. Now, we've got some algebra to do. Get rid of that 8,000 first by dividing by 8,000. What you do to one side, you have to do to the other. So 18,504 divided by 8,000 is 2.313 equals. Now, that got rid of the 8,000. 0.06 divided by 2 is 0.03. 1 plus 0.03 is 1.03 raised to the 2t. Now, you might be wondering, what do you do from here? It kind of looks unfamiliar. Well, it might look a little bit more familiar to you if you switched these two things around. Let's go 1.03 raised to the 2t power equals 2.313. And now we're going to have to go into log form because I can't get a common base. So I'm going to introduce logs. So the log of 1.03, I'm going from exponential form to log form. So the log base 1.03 of 2.313 equals 2t. So again, one more time, I went from exponential form to log form. Now, the way to get t by itself right here would simply be divide both sides by 2. And that would mean t equals, because the 2's would cancel, t equals log base 1.03 of 2.313 divided by 2. So if we were asking for an exact answer, that would be the exact answer. But we're not. We want to actually know, something that is more meaningful than this. So we're going to need to change the base. We're going to use the change of base theorem on this numerator to make the numerator be log 2.313 over log 1.03, and then we're going to divide that whole thing by 2. And now is where your calculator comes in. You can do all of this on your calculator. Let's do the numerator first. The log of 2.313 divided by the log of 1.03. Close your parentheses, hit equals, and that's what my numerator is, that long answer. Now I'm going to divide that by 2, and there's my answer. Let's round it to a tenth, so that would be the time is approximately 14.2 years. So time is approximately 14.2 years. Let's move on to another concept that's floating around in this objective, and that's the idea of continuous compounding. In some books, it's called instantaneous compounding. What it is just in this fast computer age, it can be done, in fractions of a second. So that's what they're talking about. It is just continuously compounding. There's another formula you would use for that. A equals P times E raised to the R times T power. Obviously, you can see E is in this formula, whereas it wasn't in the other one. So here's example 3. An investment of $1,500 is made into an account which pays 5% interest, which is compounded continuously. How much will this investment be worth after 6 years? So I'm still wondering what's the final amount after 6 years. So we still are solving for A. A equals the principal amount. How much did we put in the first place? Is still 1,500. E is E. And then raised to the R times T. Well, the interest rate is 0.05. And the time is 6 years. So A equals 1,500 multiplied by E raised to the 0.05 times 6, which is 0.3. So now, the rest of this can be done by the calculator. I'm going to use the E raised to the power button, which is, on this calculator, it's the second function of the natural log button. So second natural log, you can see you get your E, and it's already asking what power do you want me to raise E to. I want it raised to the 0.3 power. And that's what you get. And now I want that multiplied by 1,500. And I get $2,024 and approximately 79 cents. So A is approximately $2,024 and 79 cents. The final problem is another continuous compounding interest problem, but this time we know what we end up with. How many years will it take the investment from example number 3? So the initial investment was $1,500, $1,500. How long will it take it to double, to become $3,000? So we know the ending amount we want is $3,000. We also know the beginning amount was 1,500. E is E. Now remember the interest rate in that previous problem was 5%, 0.05, and this question is wanting us to solve for the T. How long is it going to take for that to happen? Well, the first thing again that I'm going to do is I'm going to get rid of that leading coefficient. So I'm going to divide both sides by 1,500. So the left-hand side now simply becomes 2. And on the right-hand side, the 1,500 disappears. Now I only have E raised to the 0.05 T. Again, if it looks a little unfamiliar to you, look at what it would be if you switched everything to the opposite sides. E raised to the 0.05 T equals 2. Now, I'm going to go into log form. I'm going to go from exponential form into log form. But this time, since my base is E, what it's going to turn into is the natural log. So the natural log of 2 equals 0.05 times T. Now all I have to do to get T by itself would be divide both sides by 0.05. So T equals the natural log of 2 over 0.05. And this is going to be rather easy to do on the calculator because we're just going to use the natural log key. So the first thing we're going to hit is natural log. We're going to take the natural log of 2 and we're going to divide it by 0.05. And there's your answer. We want the answer rounded to the nearest tenth, so 13.9. T is approximately 13.9 years.